All right, so let's go ahead and review the syllabus today because we are coming close to the end here. Okay, so last week we did the bromination of stilbene, and this week we are doing dehydration of cyclohexanol. We'll review that in a moment. I want to address, so next week we're going to have like a dead week, kind of like, in classes where you get to study for finals. This is going to be the week that you have off to study for the exam. So since I was informed of that by Dr. Estokia, I decided that instead of having an ongoing kind of us running through all lab manuals and everything and it being scattered, what I'm going to do this weekend is I'm going to go ahead and create a full review video that'll be probably an hour, maybe 2 hours at most, for everyone to be able to view. I have a morning section today, and then obviously for your section. So I'll create that video. I'll go through each one of the lab manuals and talk about the key ideas, the key points that we learned throughout the class. And yeah, so then you'll have to review it. You'll get all of next week to review, and then the exam will be between April 26th and 30th, and I'll explain that here in a second. Finally, reminder, if you haven't done the discussion, I did notice most of both of my classes so far have completed at least the discussion portion. If you haven't completed the discussion portion, please go into Canvas, go to the discussion portion and complete it. It's a quick 5 points. If you don't use it, you lose it. And then, of course, the poster is coming closer May 1st. So, just remember, if you haven't started, get started. And yeah, this will probably be my last reminder. Maybe I'll send out an email or something regarding, the poster and everything, just so that way that y'all have, some sort of reminder towards it, because I know that it kind of has just been looming in the distance. But once again, if you haven't started, please get started on it ASAP at this point. You have about 2 weeks left for that to be due. And so what I want to talk about primarily to start before we get into the actual lecture today is the exam. So I got full clarification what's going to happen. I thought it was going to be during our class period. So what I was informed of, and it's going to be very beneficial for everyone here. So when it is anytime, and I'm just going to continuously repeat this, anytime that you want to, Monday through Friday, April 26th through 30th, as long as it's in between 8 a.m. and 8 p.m. So whatever day that you have free, if you want to do it on Tuesday at 3:30, like our normal lab period, go for it. That's totally fine. If that's just the only time you have during your week that's available for the exam, go for it. You just need to remind yourself you need to have 2.5 hours. You might not use the full amount of time, but I would recommend, have that amount of time so that way, in case you need it. And otherwise, then yeah, so you'll at any point between 8 a.m. and 8 p.m., you can start up the test. If you started at 8, I really would recommend that if you're going to start late, start at 7 at latest, because what happens is, okay, so if you start at 7, you get 2.5 hours. And from what I was informed of is that whenever you start your exam, whatever time, once it hits 11 p.m. in the system, it just shuts you out. So you want to make sure that if you're going to do the test at any point, don't let it be, closer to the end time frame. I would definitely recommend anytime between 8 to around 7-ish is my recommendation personally. That's to your own volition, and whichever time that you want to go and do it. You can do it during our class period. You can do it on Monday. You can do it on Wednesday. You can do it on Thursday, as long as it's in between April 26th and 30th, and in between 8 a.m. and 8 p.m. of that given day. You're going to take it through Examity, and I'll show you how to set up a profile here shortly. And it's going to be, you log into Canvas, you click on the Examity, it's going to connect you to their platform, and then they're going to have a proctor that's going to view as you take the exam. So at first I thought that I was going to be proctoring and it was only going to be during our class period, but plus or minus that now you can choose when you want to take your exam. It's kind of beneficial now, because maybe if you have a test or a quiz that day and you're like, Scott, I really can't take it this day, it's really conflicting, then sure, take it Wednesday, take it Thursday. But by latest, you have to take it by Friday, April 30th. That's the cutoff day. Those are the cutoff times. I don't believe there's going to be any exceptions. And if you have any sort of thing that goes on, you have to contact Dr. Rastogi. Don't contact me directly because I, can't control a final exam like that. That's the professor's final decision. So make sure at some point, Monday, Tuesday, Wednesday, Thursday, or Friday, anytime in between 8 a.m. and 8 p.m., to sit down and have 150 minutes ready for yourself to take the exam. And let me see real quick. So you don't have to. I'm not sure that if you have to sign up like for a specific time slot or anything. I think that it's going to be that you just go in and that you just take the exam. And yes, it is, Katie, but we will discuss that when we start talking about the experiment at hand. So next, the thing that I want to discuss is, let me see. Of course, you'll have to have the camera facing you. This is this way, since you're going to be doing an online test. They're going to make sure you have your academic honesty, so on and so forth. Oh, and okay, so with regards to the exam, so the way it's going to be, think about the way that you've taken your quizzes before, and what it's going to be is the same format. There's going to be, I think, like 25 multiple choice, kind of the drop-down boxes that y'all get to decide, where you like drop down and then you choose something. That's like the first portion. And then there's like a little short answer portion, just like in the quizzes where you need to take a piece of paper out, take, have a pencil out or pen, whatever that you want to use. And then you have to, take the question. Okay, this is, question 26. Okay, 26, and then you write out the answers. Okay, number 27, and you write out the answer. And then you have to scan it and upload it into there. To me, it looks like it really shouldn't take 2.5 hours, especially with the, the drop-down boxes. But allot yourself that time just in case you do need it. Rather be safe than sorry in regards to the quantity of time that you need for this exam. And yeah, so then I'm going to, of course, create that review video for everyone just so that y'all have something that you can refer to, and then you don't have to kind of jump through every one of our Zoom call videos that we had from before, because in between, sometimes I'm answering questions and it maybe is not as relevant information as it will be towards me just, going straight through a review of just going through everything. Because now once you've already gone through it once, and so going through this again, whenever you hear the information that I'm going to be, telling you in this video, I feel that you will be able to understand what I'm talking about. And whenever I tell you a fractional distillation, it won't just be like this thing that you think of like an oil rig or something. You'll understand like, what a distillation rig is, or distillation apparatus is inside of a laboratory. And so going forward, then, yeah, just to touch back to where we are again, last week was bromination. This week is dehydration of cyclohexanol. Next week, we do not have class. I'm going to provide you that video. And then the week afterwards is the week that you have to choose which day, which time you're going to sit down and take your exam. And then finally, you have your poster and your discussion closed on Saturday, May 1st at 11:59 p.m. So just remember that that is in the distance, just because, it's something that we're working together on, but that is something that I want to make sure nobody just loses points over not doing. So let me switch one moment over here. And so in Canvas, there are some tools to show you how the Examity will be set up. If you go into the files, they'll be under Exam or Examity. I'm not sure how it shows on your end, but you just go in there and there's going to be a couple files like this. So this is our test taker guide. And I just want to briefly show you it. It's very simple. I know that you've created profiles before. We all grew up in the digital age. So this is not as critical as it may seem. So I just wanted to kind of go through. They recommend using Google Chrome, and to disable your pop-up blocker. Remember that that tablets are not supported. And then, of course, it says here Chromebook, but do not use a Chromebook. Make sure you're using a desktop or laptop, Google Chrome. You need the webcam, microphone, speaker. In this case, if you don't, I would assume that you need to utilize your phone as a source of video. Then, let's see, go ahead and you create your profile. Very simple, put in all of your information and put in your email to your Texas State. Upload a picture of your ID. I would assume that you'll need to do, let me check one second. Pretty sure that it said that you need the Texas State ID or driver's license. But I don't want to just say words. Oh yeah, here it is right here. Yeah, so photo ID proof, if you just have your Texas State ID, that's fine. I understand if you don't want to upload like your driver's license or passport for security measures onto, Examity. So you can just upload, your Texas State ID, and that'll be identification. Yes, you'll have to upload the PDF of that short answer portion. So that is the section that they'll allow you to utilize your phone on the exam. And then, of course, you cannot use your phone at any other point within the exam, just for academic honesty. So when you're creating this, upload a picture of your ID. If you want to use your Texas State, you can, or a driver's license. Then you're going to have to answer, 3 challenge questions for security to protect your account. Submit your digital signature. This is like if you're signing something online, and it's basically you saying, that you confirm that is your digital signature. And then your profile's created. So it's, very simple to set up. It's going to be interconnected through Canvas, and Dr. Stogie will be sending out more information. If you want, more of the manuals and such for Examity, go onto the files on Canvas under, I think it's under Examity, and then you'll be able to see exactly basically what I'm showing you here and the rest of it. So before we go through the dehydration of cyclohexanol, I want to open up our module just so that way I can show everyone where we stand. Okay, so of course the HOLA discussion poster, I've said the Examity, that'll be open on that week. And then the dehydration of cyclohexanol is what we're going to be discussing today. So let's open this up, and then I actually want to watch the video with y'all today. So I'm gonna stop share one sec so I can open it, because I actually opened it for the morning class. So I want to have this ready for when we watch, so that way I can show you the glassware. Let me just open this, and I have one more video as well that I wanted to show everyone. Okay, great. Now let me switch back here. If your computer has a webcam, one moment. Sorry, the chat box disappeared. And I don't know if the quality of your webcam will be good enough to upload, because if it's illegible, then that will be an issue. I would recommend to take your phone and to scan it, because if you try to use your webcam and it's not good quality and I can't read it, that's going to be we're going to have an issue there. So I would recommend to utilize your cell phone as a camera, using Adobe Scan, and then upload it, and then get it into your email or whichever way that you need to get it into your computer and upload it into the Examity. So going into here, this is the experiment we're covering this week. Of course, we're going to be reviewing the lab manual. Go ahead and watch videos 2, 3, and 4 at your own time to review this. And then, of course, completing the quiz and, the rest of the notebook and such. So since we're going to spend most of the time on going through the video together, I'm going to go ahead and jump into our lab manual so that we can discuss the reaction we are going to be reviewing today. And it's not going to be anything novel in terms of what you've already learned in this class, because this is let me see, who was it that was mentioning? As Katie was mentioning, dehydration is an E1 mechanism, and it is formation of a carbocation. It is E1. E2 would mean that you would have elimination, but it would be just like SN2, and it would be bimolecular. It would just go immediately, and it would just be done, and you would immediately get your alkene or double bond, whichever way that you want to say it. So firstly, to start off, the dehydration of alcohols occurs under acid catalyzed conditions in order to form alkenes. So what this means is, in the presence of a Bronsted acid, such as sulfuric or phosphoric acid, dehydrations involve the initial protonation of the hydroxyl group. So do you remember this from whenever we were using acid in order to create a carbocation? This is the same thing as in SN1. So SN1 and E1 reactions, you may see them in your organic class, and they're very similar in certain ways. However, in this instance, what happens is, so firstly, we know the proton comes in, it protonates our alcohol group, right? And so the loss of water then takes place in a unimolecular process. So then the water group leaves. So we remember this from SN1. Well, in E1, it's in the same way. Water's leaving, and what happens is we're left with a nice carbocation. So what can happen is then this hydrogen here can actually donate its electrons to the pi cloud that is between the two carbons in order to create this alkene. So, as they say here, loss of water then normally takes place by a unimolecular process, resulting in high reactive carbon that can stabilize itself by the elimination of a proton from an adjacent carbon to give the alkene. So we have our adjacent proton here, an alpha proton, whichever way that you want to call it, and then it actually donates its electrons and it leaves as a proton, and then you are left here with an alkene. So we turn our alkane with an alcohol group into an alkene. Very straightforward reaction. And another thing that we want to kind of cover here that isn't as relevant within what we're discussing, but it is relevant in chemistry, is that carbocations can also rearrange by alkyl and or hydride shifts to form more stable cationic species than they yield the other alkenes. So you probably know that in organic chemistry you have major products, minor products. Well, in the instance here, we have two minor products and our major product. The reason being is that if you look here, this alcohol here is a secondary alcohol in this case because we have two carbons bound, but then we only have a hydrogen there. So what happens is that, as we know with carbocations, the most stable carbocations are tertiary carbocations. Then we know, of course, it goes in the reversing trend that secondary would be less stable, and then primary would be extremely unstable, almost impossible to create. And as you see here, only 0.4% of a primary alkene was created, and that would be if the alkene actually shifted, or if the carbocation shifted over to the last group. That would be the only way that we can actually create this. And otherwise, the major product would actually be if we had a 1,2 alkyl shift. So what happens is that the proton is created here. So our alcohol leaves out of here as water. We're left with our carbocation. And what happens is we experience this thing called a 1,2 alkyl shift. So the alkyl group actually just moves over and takes the place in order for that carbocation to go to a more stable location. So where it would be here is, since this would be moved here, then the carbocation would be in a secondary position instead of in this sort of secondary-esque primary position. So then the major product here would be if this carbocation shifted over one, or if the alkyl group shifted over one, and then you create an alkene right in the center. And if you think of it, that is like a more stable, more less steric hindrance. Everything is nice and stable in the center. Secondly, you can have this here, which would be, there is still the 1,2 alkyl shift. However, we have an alkene here that is secondary. And then here is the worst one, which would be a primary alkene. So this is extremely unfavorable. And as you can see, it's only 0.4% yield. And then the secondary alkene is over here at 20% yield. And then this would be sort of a tertiary-esque alkene. It's the most substituted that the alkene can be without breaking our 8-electron rule. So that is the main key idea I wanted to get around here, just to let y'all know about the 1,2 alkyl, 1,2 hydride shifts, since it's not as relevant in the reaction that we're performing, but this is just some information that they're giving towards if you were performing it, let's say on something like butanol, ethanol, or propanol, something that has a longer chain of carbons. And so finally, another little portion here, and they kind of run off on a tangent in this lab manual, so I didn't really want to get too deep into the rest of this information, but just to quickly cover, iodine, alumina, molecular sieves, and ion exchange resins can all act in order to create alkenes as well. And dehydrating agents such as POCl3 and acetic anhydride can all be used to perform eliminations. But again, this is kind of just extra information that's not as relevant within your lab notebook. So it's just good to have a little note there for everyone to know. And then finally, so we're going to synthesize cyclohexene from cyclohexanol. And then afterwards, just like we did in the previous lab, we're going to confirm the presence of an alkene using a bromine test. So we didn't use the bromine test last time, but we used the silver nitrate test, we use the sodium iodide test, we use these other chemical tests where we have some sort of reagent that reacts readily with this group. And if you think into the bromination lab, what did we have? We had an elimination addition reaction for the bromine to come in onto a double bond. So it's kind of, Everything in chemistry is kind of cyclic in nature, comes back to itself in order to kind of prove itself in the scientific method. And so I'm not going to read through this procedure. Just make sure to write it in your own words because we're going to watch the video here shortly. And then make sure, of course, to go ahead and answer the post-lab questions. And we'll cover the data once I get through this video with everyone. So let me go ahead and switch over to the video so that way that everyone can see a preview of how this reaction would be set up. Okay, so, here is our reaction conditions. We're going to have cyclohexanol right here. So it's a cyclohexane ring with an alcohol group attached. We're going to have 85% phosphoric acid or concentrated phosphoric acid. The conditions of the reaction are to boil at 100 degrees Celsius for 10 minutes, and then you will create your product of cyclohexene. And then okay, so firstly, the dehydration of alcohol is acid catalyzed. In order to do this, we need to form a carbocation. Then we perform the elimination of a proton, which results in the alkene product. And then this avoid acid contact is just a note for in lab that you want to make sure not to harm yourself by coming in contact with acid in lab. Just make sure to wear your gloves. If you need to, wear your lab coat. Okay, so here's our mechanism. We protonate our alcohol group. Once the alcohol group is protonated, like forming water, H2O, it leaves in the dehydration mechanism. The carbocation is formed, and then our proton can donate its electrons over in order to give us our alkene, just like we discussed. And then these are some extraneous things. Of course, calculating percent yield. We're going to perform the bromine test. Other methods of analyzing the product would be to perform gas chromatography, IR, NMR, et cetera, et cetera. And we don't have to worry about the other ones there. This is just talking about the other extraneous things that you would have. Okay, and so here we're going to set up the reaction where we have a round bottom flask, the boiling stones in there, we have our reactants in there, attached to a fractional distillation column, and we're going to be running the reaction at 100 degrees Celsius. And you're probably wondering, why are we using fractional distillation column? What's going on here? Don't we just run a reaction in a flask using a condenser and it just refluxes and that's it? Well, we'll get to that here shortly. And this is a key idea here that's a really cool concept in chemistry that is very helpful for this reaction and for reactions at any point that you may be running. So I'm going to kind of skip through here, and because we already know how the setup is of a distillation apparatus. So going forward, we have our two-phase separation afterwards in order to wash our organic phase, remove any excessive water, just so that way we only have cyclohexene in our product. Okay, and so here's all of our glassware and everything. And I'll run through this one more time just so that way, let me get it paused. Okay, so, all right, so here we have our Erlenmeyer flask. I would say about 150, 250. And then we have our distillation apparatus. So that's going to consist of a condenser. We're going to have our adapter, and we're going to have our thermometer, the thermometer head. You're going to have the vacuum receiving adapter, and then you're going to have your graduated cylinder. You're going to have your keg clamps, and then you're going to have your separatory funnel here, and you'll have another condenser. So I would write down 2 condensers, and also make sure to write down the boiling stones. Oops. Have your boiling stones written down, and your rubber hoses, and your round bottom flask. And that'll be all of the items that you'll utilize within the experiment. Always you can refer to, if you need to know the glassware you would utilize in a distillation system, just search up distillation apparatus, and then that way you can go through and list out each item that you would be utilizing within it. Just please do not only write distillation apparatus, because in that instance, that's not good enough. You need to be able to walk in with a lab notebook and perform the experiment, like I've said. So what we do here is we're going to go ahead and take the cyclohexanol, and this is an important thing that you probably already went through in Gen Chem labs, I would assume, and that is utilization of density. But I wanted to briefly cover it for a second so that everyone can get a look in case you needed a quick review. Let's see if I can. Okay, no, it's still 40. Anyways, So when we utilize density, what does that mean? So density, everything has a certain density to it. And liquids, in this instance, cyclohexanol, that has a certain density. For every milliliter, there's a certain amount of grams per milliliter. So that is where we utilize density, because what happens is we don't have a powdered substance in this case, right? We have cyclohexanol in a bottle. It's a liquid, just like ethanol is a liquid. So what we need to do is, the easiest way for us to measure this out without having to put a flask onto a scale is for us to actually pour it into a graduated cylinder and utilize a specific amount of milliliters of the liquid. So instead of having to, clumsily take a flask and try and pour it on top of a scale, maybe you spill a little bit, and then all of a sudden, you've caused all of this trouble. So instead, what you can do is you're going to take the density of cyclohexanol and perform the conversion. So what you do is, as we know in algebra, you can move over variables of x and y if they're equivalent on each side. So density is equal to mass over volume. That means that volume is equal to mass over density. So what you can do is you can take the volume here and then you can make it equal to mass divided by density. And so in this case, the mass of cyclohexanol is 10 grams. And in this case, the density is 0.962 grams per milliliter. So when you divide the 10 grams by the density, then you end up with 10.4 milliliters. And the reason that these two here are written as 5 and 5.4 is because we're utilizing a 10 milliliter graduated cylinder. So whenever you're doing that, in order to be accurate, you want to measure out firstly 5 milliliters, add it to your round bottom flask, and then you measure out 5.4 milliliters, just because if you tried to measure out a full 10.4 in a 10 milliliter, it doesn't go that high. So you just want to make sure 5 milliliters first and then 5.4. Add it 2 times and then you're good to go. So I just wanted to do that quick review of density in case anyone was a little, foggy on density from the past. So you take your mass divided by the density, and then you're left with the milliliters of your compound, and they are equivalent. 10 grams of cyclohexanol is equal to 10.4 milliliters of cyclohexanol. Okay, so skipping through, all they're doing here is measuring it, adding it, and then to get to that last mark of 5 milliliter, you would want to add dropwise very slowly, so that way you get your meniscus just to the 5 milliliter mark. Okay, adding it in, we're going to skip through here. Okay, and then now inside of our ventilation hood, we have our concentrated phosphoric acid, or 85%. Just got to take 5 milliliters and add it in there as a reagent. Okay, so now we're at 5 milliliters here. I'm going to go ahead and add it in. Very simple. All you have to do is add the cyclohexanol and the phosphoric acid together. Then finally, she adds in the boiling stones into the round bottom flask before we start heating up this experiment. Okay. Oh, and then also you have your electric heating mantle here, or whichever way that you want to call it. Just make sure no Bunsen burners. Additionally, always add a little grease around any joints that you add together in any sort of heated experiment, because glass can expand and you don't want it to crack. And I always say it as a reminder, because certain things, whenever you're inside of a lab, especially since we're not performing it, you can kind of forget them. And I just like to remind students, because safety is the #1 concern whenever you're inside of a lab. We're here to learn things, but also we want to make sure that nobody gets harmed in the procedures. So now that everything's set up, we start it up. And I'm going to skip over here because it's kind of just setting up everything. Okay. So right here. Okay, so now it's boiling. It's been set up. It took 15 minutes to reach the boiling point, but now you can see now it's boiling. Okay. And then up at the top, the thermometer is there and it is reading. You can see it's reading up at 100 degrees Celsius. And so you're probably still wondering as to why we have 2 condensers. Why do we have the first condenser? And then what is with the second condenser? What are we distilling? Like, why are we performing a distillation? So going forward here, there we go. Okay, now this is the critical part, so make sure you're paying attention here. So cyclohexanol's boiling point is 161 degrees Celsius. However, cyclohexene's boiling point is 83 degrees Celsius. So do you see where I was getting at with this? This is why we're performing this this distillation here on the reaction, because what happens is as we convert over our cyclohexanol to cyclohexene, we are actually distilling off cyclohexane. And this is why I was saying it's such a great method within chemistry, because then you can go ahead and, you know, boil over your product, and then you're left with the starting materials that didn't react. You're left with any sort of side product, any sort of solid materials that won't boil. And this is a very effective way of performing reactions. So this can commonly be used as long as that you're performing a reaction on something that has a lower boiling point than your starting material. So then, of course, we collect over our product. Okay, going forward, and then this is just the crude waste that we have from the starting material, and maybe any sort of side product that we have there. And so here's our crude product that's been distilled over. You have to remember, though, because we were at 100 degrees Celsius, we may have some water that came over, maybe a little bit of acid that's still left over that's come over into the receiving flask, but we don't have cyclohexanol because the boiling point is too high for that. However, it's not too high for us to have the water or acid kind of fall over into the distillation apparatus. Chat. Yes, so calcium chloride will be included in the chemicals and procedure, and 100% sodium bicarb. And you let me see how this turns out. I don't know if there's I think we may have a sodium bicarbonate wash, but let's watch this first. So right here we're taking 2 milliliters of sodium carbonate and 10 milliliters of ice cold water, and we're going to actually pour that into our reaction mixture, because what that's going to do is neutralize any of the acid that may have distilled over into our crude receiving flask. Because like I was saying, the reaction's running at 100 degrees. Anything that's boiling could be water, could be cyclohexene, and could be a little bit of acid. So we need to neutralize it coming over. And let me see, I'm not sure if they actually had sodium bicarbonate used in here, but we can check the lab manual afterwards. But let's get through the video first, and then we can jump over to the lab manual, just so we're not like jumping between screens. Either way, we're setting up here our two-phase extraction. We're just washing with a little bit of water and the sodium carbonate. Sodium carbonate is a weak base. And so this is the common utilization of a two-phase separation, a utilization of a SEP funnel. I probably reviewed this with you before, but I'm going to again. You cover your hand on one side, and then with the other hand, you're going to hold the stopcock. You turn it very lightly and then release the pressure that goes out. Always make sure it's never facing towards somebody. It's never facing towards yourself. Always face it away, up and away, in case anything comes out. It can kind of just go onto the lab bench or whatever. You just shake it very gently, turn it back up, open it, relieve the pressure, and then rinse and repeat. And then, so now we put it back onto the ring clasp, and we're going to go ahead and open up the top of the SEP funnel. Okay. And then it takes a little bit of time to separate. Sometimes some of our products are a little bit missable with the aqueous layer, so you just have to give it a little bit of time. But finally, the water starts to separate from our cyclohexene. And as you can see, sometimes chemistry can be a little convoluting because you're having these two phases sort of mixing together. But finally, we wash it off. So we have our aqueous waste, which is just this water that's washed off our acid, some sodium, some carbonate. And then, of course, yeah, we have our organic waste with our boiling stones in there from the starting materials. Okay. And so they're going to pour, oh yeah, this part I remember from this morning, they somehow he managed to duplicate the video. Okay, so right here, this is the next step. So commonly in chemistry, what we do once we've performed a two-phase separation is that we can take our organic phase and we want to put it over a drying material, whether that be molecular sieves, calcium chloride, magnesium sulfate, sodium sulfate, any sort of anhydrous solid material that can absorb water very well and actually stay there. So sodium chloride is not very good for it because, as you know, if you put salt into water, it dissolves very easily. So we want to use these more porous and larger sort of compounds like calcium chloride. As you know, calcium comes out of the tap water, and it can precipitate out whenever you pour out your water. That's why you need to filter it with Brita. So in this instance, calcium chloride is used as a drying agent. So what we do is we actually are going to go ahead and put the calcium chloride into the bottom of our Erlenmeyer flask here, and then we're going to pour the cyclohexene over the calcium chloride. And what that does is that takes the cyclohexene on top of the calcium chloride. The calcium chloride pulls all the water out of our organic phase, and we are only left with our cyclohexene. In this case, it's still slightly crude cyclohexene, which is fine, but what we want to do is remove all of the water before we perform our final distillation to get pure cyclohexene. And then here, waiting for 10 minutes, this is a common practice that you kind of want to just wait and let the water to absorb into our drying agent, whatever that be, whether it be molecular sieves, magnesium sulfate, or calcium chloride in this instance. And then finally, we're going to perform step 3, which is a simple distillation. And we can safely perform this between 80 to 85 degrees Celsius because we know now there's no more water left because we've used the drying agent. So we set up our simple distillation apparatus here. And I think that they're saying to rinse with acetone, to rinse all of your glassware with acetone to make sure that you don't have any existing residual water, because you want to know exactly how much cyclohexene that you got out of your reaction. So we decant it over, and as you can see, the calcium chloride, it just stays there. That's the really great thing about these drying agents, is that they just stay there at the bottom of your flask, and you can just pour over all your product, and then you're good to go. Okay, so you put your boiling stones in here, attach it in there, make sure to grease your joints to make sure nothing cracks whenever you heat it up and that it doesn't get stuck. Okay, now we have our boiling. We've put our thermometer down there so that we know what our temperature is boiling at. Okay, they're just setting it up. Okay, and now we're boiling it. And then we can see here that we have the temperature that's actually down in the round bottom is around 85 degrees Celsius in this instance. So the grease prevents cracking of glassware because what it does is it basically makes it more fit. So whenever I say that it can crack, it's not that if you just heat glass, it all of a sudden just cracks. What happens is that two pieces of glassware that are put together, whenever they heat, they expand the glass. So the glass that's inside of this, that's going down into the round bottom, that glass is expanding, right? And then what happens is when you cool it down, well, that glass physically has expanded. And what grease does is it actually prevents it from expanding out and sticking. So whenever this glassware heats up and expands, and then you finally take it back to room temperature, if you didn't have grease on it, you would experience that the glass would stick together. And if you try and pull glassware apart from each other that isn't greased and it's just the glass has heated up and stuck to each other, you can end up maybe like pulling it sideways and cracking it. Glass is malleable in the sense that if you push too hard on it, it is a physical thing. It will shatter. And so the grease basically gives us a layer of protection that allows it to where the two pieces of glassware don't expand into each other and basically make you crack it. And so finally, our product was about 5.4 milliliters, and then they're performing the bromine test. But I wanted to actually show a better example of the bromine test in a separate video because I liked the way that this person had done it, because they actually compare it to another compound. They don't just say, here's what it does. So in this video here, on the left, we actually have, let me take it back a little. Actually, they always do like these little weird previews. I don't know why. Anyways, okay, so on the left, we have cyclohexane. So just cyclohexane, just remember, there's no double bonds, nothing. Just cyclohexane. Just imagine the 6-membered ring. It's all alkane groups, that's all. In the middle, we have cyclohexene, which has one double bond on it. And then on the right, we have a bromine water solution. In the instance of the video that Dr. Rastogi had provided us, it was a bromine and DCM solution. It's still the same thing. If you think about it like the bromination reaction, and I'll pull that up here in a moment, it is exactly the same thing that the bromine is going to react with our alkene. So firstly, on the left, we have our cyclohexane. In the middle, we have our cyclohexene. And on the right, we have our bromine water. So on the left, we put our bromine water into the cyclohexane. And as we see, it discolors it and nothing happens. That's it. It just colors it, right? Well, in the middle here, firstly, you see there's a 2-phase separation. So that's a staunch difference between adding to that cyclohexane. And as we start to shake it together, now you see it's turning color and it's starting to go to a lighter yellowish. Now it's greenish and it's continuing to go forward. And so all of a sudden now look, we have a very not clear but white precipitate in the organic phase, and then we have an aqueous phase that's at the bottom. So what happened here? So what happened here, as you can see on the left, the cyclohexane, nothing happened. We added it in and then nothing happened. In the middle, you can see that clearly, firstly, there was a separation. Secondly, there was a coloration that's gone now. So the reason this coloration is gone is because the bromine has reacted with the double bond on that cyclohexene in order to form 1,2-dibromo cyclohexane. So let me pull up for you 1,2-dibromo cyclohexane, so that way that everyone can see exactly what we've created here in this test. Okay, so right here, before we had a double bond, it was just a 6-membered ring with a double bond. And what happened was we put the bromine into the solution, and then it reacted with our double bond in order to create 1,2-dibromo cyclohexane. And finally, I would like to show the bromination of stilbene as a reference, so that way that everyone can understand how everything kind of loops in together. And this will be the final thing that I will share for today before we wrap everything up. So like we knew before, the electrophilic addition. So in this electrophilic addition, bromine comes in, and let me come down here. So bromine came in and then forms our brominium ion, and then the backside attack happens from the other bromine. And so what happens here is that the double bond is now broken and we create a dibrominated system. So in this instance, with the bromine test, we are confirming, yes, we have dehydrated cyclohexanol into cyclohexene, and then what we do is we add in some of our liquid bromine in order to go forward to create 1,2-dibromo cyclohexane. And then that finally confirms what we've been doing the whole time. Same way with the silver nitrate test, same way with the sodium iodide test. All of these tests are reflections of chemistry within itself in order to prove that yes, this happened. So if you took cyclohexanol and you put bromine into it, nothing would happen. Unless you put it under certain reaction conditions, it won't just react in a test tube like that. But in this instance, you can see that if you put bromine with a double bond, it is ready to perform that elimination, this sort of electrophilic addition mechanism is what it would perform. So that is all that I have to share with y'all today. If y'all have any questions, please feel free to stick around. Otherwise, y'all are free to go.